This meeting is being recorded.
So let's take a look at the next type of addition reaction listed in our text. In chapter 8.8, we have what's called hydroboration oxidation. So again, this is another type of hydration reaction. So we're going to add H and OH across our double bond, but now we're going to do that with an anti-Markovnikov radioselectivity. So what that means is that our OH group will be installed on the less substituted vinylic position. So let's take a look at some more details here. And this is also, we should note, a two-reaction sequence. So we have in step 1, the hydroboration, and then in step 2, we have our oxidation. So not only are these reactions radioselective, they're also going to be stereoselective. And by that I mean that they will only add in what's called a syn addition fashion. So what that means is that in reference to the double bond, both our H and OH will add in the same plane. So you can see that if the H is on a wedge, the OH is on a wedge, or vice versa, we'll get the dash pair. So we have the H and the OH on a dash. And these will be our products. We'll always get enantiomers. So they will add in a syn fashion, and we'll get these enantiomer products, but we will not see an anti-addition, which would be a wedge and a dash of our H and OH. So these will not happen. And the reason for this is because our borane, our BH3 that is involved in this type of addition is very similar to a carbocation intermediate that we saw with other additions, right? So they're flat and trigonal planar, and they have these empty p orbitals. So what happens is borane is actually very reactive. It does not have a full octet. So two borane molecules may form what's called a dimer. So they kind of are interacting together here in this dimer that we call. So how we can stabilize this and this diborane, this dimer that forms, is using an ether solvent. So we see that here with THF, this tetrahydrofuran, this complex that's formed over here between the borane and the THF, allow this reaction to progress. So what happens is we know that it follows this anti-Markovnikov radioselectivity, and we'll briefly talk about why. So the borane here becomes reacts with 3 moles for every 1 mole. Let's go to the next slide here. So we react the borane, right? So 1 equivalent of borane will end up reacting with 3 equivalents of our alkane or our alkene. So we end up with this product here, a trialkyl borane, right? So all of these R groups are the alkyl groups that were our alkanes, or alkenes rather. And let's see on the next slide here, the reason that it follows this anti-Markovnikov radioselectivity has to do with some sterics, or some groups that might influence or block the reaction from happening along another pathway. So it has to do with what's called the transition state, right? Whether or not we have this anti-Markovnikov addition or Markovnikov addition, and we see this kind of steric hindrance or more crowded transition state that would result when we try to do this Markovnikov addition. So in the end, we see an anti-Markovnikov addition that results mainly because of this steric hindrance. So the details of both parts of this reaction, the hydroboration, right, and we end up with the trialkyl borane over here, and then the oxidation step, right, which we would see, this is in base, right, so this OH comes from our NaOH. We have our H2O2, our hydrogen peroxide over here, and it shows you step by step in the mechanism here. There's a rearrangement that occurs. We end up with a leaving group here, and in the end, we're going to end up with our final product after one last proton transfer, right? And we have this alcohol that results. So we've added H and OH across our pi bond. So not only, right, do we talk about the radio selectivity, we can also comment on the stereo specificity and the syn addition that results with hydroboration, oxidation. So again, this only adds in a syn fashion. So what that means is that they will both our additions, right, the H and the OH will be on the same face, all right, the same plane, whether it's above or below our double bond. We can see the two products that result here. So syn addition for our hydroboration oxidation. And what happens is, right, only syn addition occurs. If we create one chiral center, we saw previously we would get a pair, right, of enantiomers. A pair of enantiomers, right? And then if we end up with two chiral centers being created here, we're going to get two different enantiomers, right? We're going to get our pair of enantiomers, whereas previously we only had one enantiomer. So we'll end here. We'll look at some examples from the textbook from section 8.8, and then we will continue with 8.9 next time.